Let yourself settle in for a moment. Find that comfortable position where your body can truly relax, where the weight of the day begins to lift from your shoulders. Take a slow breath in, feeling the cool air move through you, and as you exhale, let any tension drift away like smoke dispersing in the evening air. Tonight, we're going on a journey through the cosmos, not one that requires any effort from you, not one that demands your focus or your concentration. Just close your eyes if you'd like, or let your gaze rest gently on some distant, softened point, and allow the story of the universe to unfold around you like the slow opening of a flower in the earliest light of morning. We're going to explore something so vast, so incomprehensibly large, that it gently bends the mind in ways that are almost pleasant, the way a particularly beautiful piece of music bends your sense of time without your noticing. Don't worry about memorizing numbers or holding on to every detail. Let the words wash over you the way a warm tide washes over the shore. Some of it soaking in, some of it receding, all of it somehow leaving you changed by the time it's done. This is a story about discovery, about a young Dutch astronomer sitting at his computer on an ordinary afternoon and stumbling upon something that no human being had ever seen before. It's a story about the enormous patience of the universe, which has been building this thing in the dark for billions of years, waiting for someone to finally look. And it's a story about the largest structures that any single galaxy has ever created. Structures so enormous that they challenge the very language we use to talk about size. So, settle in, let your breathing slow, and let's drift together into the depths of space, where giants beyond all imagining are still growing in the dark. The man who found a giant. There's something quietly poetic about the way most great discoveries happen, not with triumphant fanfare and deliberate searching, but sideways, almost accidentally, while someone is looking for something else entirely. The discovery of Alcyoneus, the largest radio galaxy structure ever recorded at the time of its finding in 2022, happened in exactly this way. Martijn Oe was a graduate student at Leiden University in the Netherlands when it happened. He hadn't set out to find the biggest galaxy anyone had ever seen. He was working on something far more subtle and slippery, trying to detect the cosmic web, that enormous gossamer network of filaments and voids that threads through the universe like the most intricate lacework ever conceived. The cosmic web had been theorized for decades. Astronomers knew it had to be there. Simulations of the universe's evolution produced it consistently and beautifully. But actually seeing it, detecting the faint gas and tendrils of matter that weave between galaxies across hundreds of millions of light years, that was another matter entirely. It was the kind of research his supervisors Hube Rutgering and Reinout van Vieren had dedicated significant parts of their careers to pursuing. It was, as Oe himself acknowledged, risky research. There was a genuine chance, going in, that the cosmic web simply wouldn't show up in the data. To understand how Oe was going about this, you need to know something about the instrument he was using. LOFAR, which stands for Low Frequency Array, is not a telescope in the way most people picture one. There's no single dish, no rotating mount, no cathedral of steel and glass pointing at the sky. Instead, LOFAR is a distributed system of roughly 20,000 small antennas scattered across the European landscape, from the marshy nature reserves of the northern Netherlands, where the core of the array is based near the village of Exloo, all the way out to stations in Germany, France, Sweden, Great Britain, Ireland, Latvia, and Poland. When you visit one of these LOFAR stations, The antennas look almost unimpressive up close. Simple crossed dipoles, about as tall as a person, arranged in fields and clusters. They have no moving parts. They don't track the sky mechanically. Instead, they listen in all directions at once, and the intelligence lives entirely in the supercomputers that receive their data. What LOFAR does is operate in the low-frequency radio range, between 10 and 240 megahertz, the same frequencies used by FM radio stations, though for entirely different purposes. At these frequencies, which had been largely unexplored by previous generations of radio telescopes, the universe looks completely different. Dust and gas that would block an optical telescope pose no obstacle. Objects that are invisible or merely faint at visible wavelengths blaze with radio brightness. And, crucially, for the story we're telling tonight, LOFAR is extraordinarily sensitive to the kind of large, diffuse, extended radio structures that giant galaxies create. Structures that previous instruments might have missed entirely because they were too spread out and too faint to catch. OA was reprocessing LOFAR survey images using new techniques designed to strip away the bright, compact radio sources that clutter the data and reveal the faint, extended emission hiding beneath them. It was painstaking, computational work, the kind that requires patience and a tolerance for the long stretches of quiet between discoveries. He described looking at the processed images immediately, curious and a little anxious, knowing there was a real possibility that all this work would yield nothing particularly remarkable. And then, there it was. In the data, a radio structure appeared that didn't match anything he'd been expecting. It was the classic shape of a radio galaxy. Two enormous lobes of Hoey ran a quick calculation to estimate the time it would take for the radio emission to reach the surface of the planet. He found that it would take approximately 100 years for the radio emission to reach the surface of the planet. OE ran a quick calculation to estimate the structure's physical size, using the measured angular extent of the source and the known distance to the galaxy at its center. The answer he got back was approximately 5 megaparsecs. Now, a megaparsec is one of those units that exists in astronomy precisely because the universe demands such things. 1 megaparsec equals roughly 3.26 million light-years. 5 megaparsecs, the preliminary estimate for what he was looking at, works out to approximately 16.3 million light-years from one tip to the other. OA, by his own account, wasn't yet certain what that meant in the context of the known record holders. His knowledge of the radio galaxy literature was still developing at that stage of his doctoral work. He sent an email to Martin Hardcastle, one of the world's foremost experts on radio galaxies and a co-author on the eventual discovery paper, describing what he was seeing and asking for a sanity check on his numbers. Hardcastle's reply was immediate and unambiguous. Congratulations, this is the largest radio galaxy ever found. The discovery was serendipitous in the truest possible sense. OA had been trying to detect the cosmic web. He stumbled upon the largest known structure created by any single galaxy instead. The universe, in its characteristic way, had revealed a secret while he was looking somewhere else. Later, when asked about the moment of recognition, he described the excitement of checking his calculations again and again. The restless energy of someone who suspects they may have found something extraordinary, but won't let themselves believe it until they've been sure 3 times over. The galaxy that hosts this structure was given the dry, cataloging designation SDSS, J08142 1.68 plus 5 22410.0, a set of coordinates in the Sloan Digital Sky Survey. But Oyoyao and his team also gave it a name that felt commensurate with its proportions: Alcyoneus, after a figure from Greek mythology. In the ancient stories, Alcyoneus was one of the Gigantes, the giant offspring of Gaia and Uranos, who was said to be immortal as long as he remained on his native Earth. He was so fearsome that even Heracles struggled to defeat him. Only by dragging him off his native ground could the hero strip him of his immortality. The name was fitting for a radio structure that seemed in some ways to be drawing its impossible size from the specific ground, the specific thread of the cosmic web on which it resided. Alcyoneus lives in the constellation Lynx, one of the fainter, less visited regions of the northern sky. It resides approximately 3.5 billion light-years from Earth. When the radio waves were now detecting left Alcyoneus, the Earth was a fundamentally different place. Life was confined to the oceans. The great evolutionary innovations, the colonization of land, the development of complex organisms, the eventual emergence of vertebrates, mammals, and hominids, all of that still lay hundreds of millions of years in the future. The light has been traveling toward us for longer than multicellular life has existed on our planet. The discovery was announced in February 2022 in a paper published in the journal Astronomy and Astrophysics. And while Alcyoneus has since been exceeded in scale by subsequent discoveries, more on that shortly, its original detection remains a landmark moment, both in the science of radio galaxies and in the broader human project of understanding how large and how varied the structures of the universe can be. Understanding the scale. To appreciate what we're actually talking about here, we need to spend some time with the numbers, not rushing past them, but dwelling in them, feeling their weight. The universe is generous with scale, and tonight we're going to let ourselves be properly overwhelmed by it. Begin with light itself. Light moves faster than anything else in the universe, approximately 186,000 miles per second, or about 300,000 kilometers per second. This number is so large that it barely registers, so let's approach it from a different angle. In the time it takes you to say the word now, light has already traveled about 186,000 miles. In 1 second, it could circle the Earth's equator more than 7 times. The speed of light is, in every practical sense, instantaneous on any human scale. Yet, when we talk about the universe, we're forced to use it as a measuring stick, because without it, we have no frame large enough to hold what we're describing. A light year is the distance light travels in a full year. That works out to approximately 5.9 trillion miles, approximately 9.5 trillion kilometers. That is the distance light covers at 186,000 miles per second, operating continuously for 1 full year. It's an almost surreal number to hold in your mind. Our sun is about 8 light minutes away. That means when you look at the sun, please don't do this directly, you're seeing it as it was 8 minutes ago. The light making that journey started its trip around the time you might have been checking your messages before going to bed. The nearest star system to our sun, Alpha Centauri, is about 4.2 light-years away. The fastest spacecraft humanity has ever built, the New Horizons probe that visited Pluto, travels at roughly 36,000 miles per hour. At that speed, it would take about 78,000 years to reach Alpha Centauri. We are very, very far from the stars, even the closest ones. Now, let's scale up to the Milky Way, our home galaxy. The Milky Way is a spiral galaxy, broadly shaped like two fried eggs placed back to back, with a central bulge of older stars and graceful spiral arms extending outward and curving through space. It contains somewhere between 200 billion and 400 billion individual stars. Some of those stars are almost certainly orbited by planets. Many of those planets are likely rocky and warm. The Milky Way stretches approximately 100,000 light-years from edge to edge. Our Sun sits about 26,000 light-years from the galactic center, tucked into a modest spur called the Orion Arm. Neither in the thick of things nor on the remote fringe, just living quietly in the suburbs, as it were. To cross the Milky Way at the speed of light would take 100,000 years. To put that in human terms, if you started your journey across our galaxy when anatomically modern humans first appeared on Earth, roughly 300,000 years ago, you still wouldn't be halfway across. All of recorded human history, from the earliest written tablets of Mesopotamia to the digital age we inhabit right now, spans approximately 5,000 years. That's 5% of the time needed to travel from one edge of the Milky Way to the other, moving at the fastest possible speed in the universe. Now, step back further. The Milky Way is not alone. It belongs to what astronomers call the local group, a gravitationally bound collection of more than 50 galaxies spread across a region roughly 10 million light-years across. The largest member of our group is the Andromeda Galaxy, which sits about 2.5 million light-years away. On a clear, dark night, far from any city lights, you can see Andromeda with your naked eye. A faint, elongated smudge in the constellation Andromeda, visible mostly in peripheral vision. What you're seeing is the combined glow of approximately 1 trillion stars, all at once, across 2.5 million light-years of intervening space. The photons reaching your eyes left that galaxy before our genus Homo had yet evolved. The distance to Andromeda is significant in another way. It's approximately 25 Milky Way widths. If you imagined our galaxy as a dinner plate, the nearest large neighboring galaxy would be more than 25 dinner plates away. Space between galaxies is not merely empty. It is spectacularly, almost offensively empty by any human standard. Now, with all of this as context, consider Alcyoneus. Its radio lobes stretch approximately 16.3 million light-years from one tip to the other. Not 16 light-years. Not 16,000 light-years. Not 16 million times the distance to Alpha Centauri, which would still be unimaginably vast. 16.3 million light-years from end to end. To equal Alcyoneus's span, you would need to line up approximately 163 Milky Way galaxies, each one containing hundreds of billions of stars, each one spanning 100,000 light-years, placed end to end in a row. Consider that the entire distance from the Milky Way to the Andromeda Galaxy, 2.5 million light-years, fits inside Alcyoneus more than 6 times. You could fit the entire local group within Alcyoneus with considerable room to spare. In fact, if you placed one edge of Alcyoneus at the Milky Way, the other edge would extend so far past Andromeda that the Andromeda Galaxy would be a relatively modest feature somewhere in the middle portion of the structure. Here is another way to feel the scale. Imagine you could stand at one tip of Alcyoneus and turn on the most powerful beacon ever conceived, a light bright enough to be visible across the entire structure. Then you begin waiting for the light to reach the other side. You would wait 16.3 million years. In that time, if human civilization continued at its current pace of development, our species would have transformed itself beyond recognition. the continents would have shifted. Ecosystems would have turned over many times. Languages, cultures, religions, empires, all gone, replaced by generations of replacements we can't begin to imagine. And through all of that, the light would still be traveling, still moving at 186,000 miles per second across the interior of what a single galaxy produced. Before Alcyoneus's discovery, the scale conversation around large galaxies tended to focus on objects like IC1101, a supergiant elliptical galaxy about 1 billion light-years away in the constellation Virgo. IC1101 is genuinely immense in terms of its stellar content. It contains something in the range of 100 trillion stars, roughly 1,000 times more than our Milky Way, and it sits at the heart of a rich galaxy cluster. Its central supermassive black hole is thought to have a mass somewhere between 40 billion and 100 billion times the mass of our Sun, making it one of the largest known black holes in the observable universe. In terms of the visible, star-containing extent of the galaxy, it stretches perhaps 4 to 6 times wider than the Milky Way. But Alcyoneus operates on a different level entirely. What makes Alcyoneus extraordinary isn't the size of its stellar disk or the mass of its central black hole. In fact, the galaxy itself, the actual stellar object at the center of the structure, is rather unremarkable. Its stellar mass is around 240 billion solar masses, and its central black hole weighs approximately 390 million solar masses. By the standards of giant radio galaxies, these are actually on the lower end. What makes Alcyoneus extraordinary is what it has done to the space around it over millions of years through the activity of its central black hole. The radio lobes aren't composed of stars. They're composed of something far more exotic: the nature of radio galaxies. To understand what Alcyoneus truly is, and why its discovery matters so deeply to our understanding of the universe, we need to spend some time exploring the nature of radio galaxies, what they are, how they work, and why the physics that drives them is among the most extreme anywhere in the cosmos. At the heart of the story is the supermassive black hole. These objects, which sit at the centers of most large galaxies, including our own Milky Way, are not just large black holes. They are qualitatively different from the stellar mass black holes that form when massive stars die. A stellar mass black hole might contain 10 or 20 times the mass of our Sun. A supermassive black hole contains millions or billions of times that mass, all compressed into a region no larger than our solar system, and often significantly smaller. The black hole at the center of the Milky Way, known as Sagittarius A star, contains approximately 4 million solar masses. That sounds enormous, and it is. But compared to some of the objects at the centers of more active galaxies, it's relatively modest. The black hole powering the radio lobes of Alcyoneus weighs approximately 390 million solar masses, nearly 100 times more massive than Sagittarius A star. And in some of the most extreme radio galaxies ever observed, central black holes can weigh 40 billion, 60 billion, even 100 billion times the mass of our Sun. These aren't merely large objects. They are gravitational dominators on a scale that seems almost absurd. A black hole is, at its most fundamental level, a region of space-time where gravity has become so overwhelmingly strong that not even light can escape once it crosses a certain boundary: the event horizon. Inside that boundary, the laws of physics as we normally understand them cease to apply in any straightforward way. The singularity at the center represents a point of infinite density, a place where our equations collapse into gibberish, telling us that something more profound is happening than our current theories can describe. But here is the thing that surprises many people. Black holes, despite their fearsome reputation as cosmic destroyers, are actually very selective eaters. The vast majority of matter in a galaxy orbits the central black hole at perfectly safe distances, just as the Earth orbits the Sun without falling into it. Gravity isn't pulling everything toward the center. It's creating the conditions for stable orbits that can persist for billions of years. Only when something disrupts those orbits, a galactic merger, perhaps, that sends enormous clouds of gas and dust tumbling toward the center, does the black hole get a significant meal. When gas does fall toward a supermassive black hole, it doesn't plunge straight in. Angular momentum won't allow that. Instead, the infalling material spreads into a flattened, rotating structure called an accretion disk, a vast, superheated ring of gas and dust swirling around the black hole at extraordinary speeds, creating tremendous friction as inner and outer layers rub against each other. This friction heats the disk to temperatures of millions of degrees. The disk glows across the entire electromagnetic spectrum, from radio waves to visible light to X-rays, often outshining every star in the host galaxy by a factor of hundreds or even thousands. When a galaxy's central black hole is actively feeding in this way, we call the resulting brilliance an active galactic nucleus, or AGN. Now, here is where the story gets genuinely strange and wonderful. Not all the material that falls into an accretion disk ends up falling into the black hole. Some fraction of it, perhaps 5 to 10%, gets caught up in the extraordinary magnetic fields that the spinning black hole and its accretion disk generate. These magnetic fields, twisted and amplified by the relentless rotation of everything in the system, act as a kind of cosmic particle accelerator. They seize material from the innermost regions of the accretion disk and sling it outward with incredible violence, not randomly in all directions, but focused into two narrow collimated beams pointing perpendicular to the plane of the disk, aligned with the black hole's rotational axis, one beam going up, one going down, like two fire hoses pointed in opposite directions. These beams are what we call relativistic jets. The material in them moves at staggering speeds, often exceeding 99%, or even 99.9% of the speed of light. At these velocities, Einstein's theory of special relativity becomes critically important for understanding the jet's behavior. Time dilates. Lengths contract. The relativistic beaming of radiation changes how the jets appear to us depending on their orientation. The physics of these jets, their formation, their structure, and their interaction with the surrounding environment represents one of the most active and contested areas of research in modern astrophysics. Two theoretical frameworks have been developed to explain how black holes launch these jets. The first, proposed by Roger Blandford and Roman Znayak in 1977, focuses on the spinning black hole itself. In this model, the rotation of the black hole and rotating black holes do genuinely drag the space-time around them in a phenomenon called frame dragging, one of the stranger predictions of general relativity, can be tapped as an energy source. Magnetic field lines threading through the black hole's event horizon act like the wire in an electrical generator, and the rotation of the black hole drives currents that ultimately power the jets. In essence, The black hole's spin is being slowly bled away to power the outflow. This is not a perpetual motion machine. The black hole really does slow down, very gradually, as it gives up its rotational energy to the jet. The second mechanism, proposed by Blandford and David Payne in 1982, focuses on the accretion disk rather than the black hole itself. Here, magnetic field lines anchored in the rotating disk act like the spokes of a spinning wheel, flinging material outward along the field lines through centrifugal effects while also collimating the outflow. In reality, most astrophysicists believe both mechanisms operate simultaneously, with their relative contributions depending on the specific properties of the black hole and disk in question. The jets that emerge from this process can travel vast distances, hundreds of thousands, millions, or, in the case of Alcyoneus and the other giants we're discussing tonight, literally millions of light years, before their energy is finally dissipated. As the jet travels, it plows through the surrounding gas, which first resists and then gradually gives way, creating a turbulent mixing zone at the jet's leading edge. Eventually, the jet's energy is spread into an enormous diffuse cloud of hot plasma, the radio lobe. These lobes consist of electrons and other charged particles moving at close to the speed of light, threaded through by magnetic fields. When these relativistic electrons spiral around the magnetic field lines, they emit a specific kind of radiation called synchrotron radiation. Named for the particle accelerators, synchrotrons, where this process was first studied in laboratories, synchrotron radiation is strongest at radio frequencies, which is why we can detect these lobes with radio telescopes like LOFAR. The plasma in these lobes is almost incomprehensibly tenuous. If you could somehow stand in the middle of one of Alcyoneus's radio lobes, which would be a strange experience, given that there's nothing to stand on, you might encounter only a few particles per cubic meter. By comparison, the air in the room where you're relaxing right now contains roughly 1,000 times 10 to the 25th power molecules per cubic meter. The best vacuum we can create in a laboratory on Earth still contains millions of particles per cubic meter. Alcyoneus's lobes make our best laboratory vacuums look positively crowded. And yet these incredibly tenuous structures are energetically significant. They contain magnetic fields, cosmic ray particles, and energy equivalent to the combined output of trillions of suns spread across millions of light years. The Fanaroff-Riley classification system, developed by Bernard Fanaroff and Julia Riley in 1974, gives astronomers a useful framework for categorizing radio galaxies based on their structure. Class 1 radio galaxies, FR1 in the notation, tend to be brightest near their centers, with jets that gradually fade and spread into diffuse plumes as they move outward. They tend to be found in rich galaxy clusters, where the surrounding gas is dense enough to slow and disrupt the jets before they can travel too far. Class 2 radio galaxies, FR2, show the opposite pattern. They are brightest at their outer edges, where the jets terminate in bright concentrations called hotspots. These hotspots are the visible signatures of shocks, places where the still supersonic jet material abruptly slams into the surrounding gas, creating a brilliant flash of synchrotron emission before the energy dissipates into the growing lobe behind it. Alcyoneus is an FR2 galaxy, and so is Porphyrion, the even larger structure we'll meet shortly. The Puzzle of Alcyoneus. Knowing all of this about radio galaxies makes the specific puzzle of Alcyoneus more interesting, not less. Because if you were to try to predict what kind of galaxy would grow to 16 million light-years, your prediction would probably be wrong. You might guess, it must have an unusually massive black hole, because a bigger engine can power a stronger jet. But Alcyoneus's black hole, at 390 million solar masses, is actually below average for giant radio galaxies. Its neighbors in the giant radio galaxy population often have far more massive central engines. You might then guess, it must have an unusually massive host galaxy, with an enormous reservoir of stellar matter to donate to the black hole over time. But again, Alcyoneus's host galaxy is on the lower end of the mass distribution for giant radio galaxies. With a stellar mass of about 240 billion solar masses, it's not a puny galaxy by any means, but it's far from the heaviest hitters in the population. Perhaps then the jet power itself is extraordinary. Maybe Alcyoneus's black hole is particularly efficient or particularly voracious, launching an unusually energetic jet. But the measurements of Alcyoneus's jet power suggest it is, if anything, slightly below average for its class. The jets that produce those 16 million light-years of radio lobes are not, by the standards of the giant radio galaxy population, particularly powerful jets. So what made Alcyoneus grow so large? The honest answer is, we don't know. The researchers who discovered it were careful to acknowledge this in their paper. They tested the three most obvious hypotheses, that an especially massive black hole, or a massive host galaxy, or powerful jets were responsible, and found that Alcyoneus falls below the midpoint of the giant radio galaxy population on all three measures. Not at the extreme low end, but clearly not at the extreme high end either. The most compelling hypothesis currently on the table is environmental. Alcyoneus resides in a filament of the cosmic web, one of those long tendril-like structures of gas and dark matter that connect galaxy clusters across hundreds of millions of light-years. The gas in these filaments is far less dense than the gas inside galaxy clusters. And if the intergalactic medium surrounding Alcyoneus is unusually sparse, if the gas in its particular corner of its cosmic web filament is thinner than average, then the jets would encounter less resistance as they expand. Less resistance means they can travel farther before they slow down, and the lobes stop growing. On this reading, Alcyoneus is record-breaking not because of what it is, but because of where it lives. There's something almost philosophical about that explanation. In this view, the remarkable thing about Alcyoneus is not its intrinsic power or mass, but the particular emptiness of its surroundings, the particular quality of the void it's been expanding into. It grew largest not because it tried hardest, but because the universe around it got out of the way. The lobes of Alcyoneus also carry a special scientific value beyond their record-breaking size. Because they're so enormous and so diffuse, with the lowest pressures ever measured in a radio galaxy lobe, approximately 5 × 10⁻⁻16 pascals, which makes the most extreme vacuums we can create in laboratories look almost cozy. They respond to their environment with unusual sensitivity. The intergalactic medium can shape and push and mold these lobes in ways that would be invisible or too subtle to detect in a more compact or more energetic radio galaxy. Alcyoneus's plumes, as one of the original discovery papers described it, perform a slow dance with an invisible partner. The invisible partner being the thin, hot gas of the cosmic web filament they're moving through. By studying how the lobes are shaped, astronomers hope to learn properties of the warm, hot, intergalactic medium that remain almost entirely undetected by any other means. Porphyrion, the record that broke the record. If Alcyoneus was a surprise, what came next was a genuine shock to the field. In September 2024, just over 2 years after Alcyoneus's discovery paper was published, the same team, led once again by Martijn Oe, now a postdoctoral scholar at Caltech, announced an even more extraordinary discovery. Using the same LOFAR survey data, now expanded to cover a larger fraction of the sky, they identified a radio galaxy jet system with an estimated physical extent of approximately 7 megaparsecs, equivalent to about 23 million light-years from one end to the other. This new record holder was published in the journal Nature, appearing on the cover of the print issue of September 19, 2024. It was given the name Porphyrion, after another giant of Greek mythology, one who rebelled against the gods themselves and was said to be the most powerful of all the Gigantes. The name feels appropriate. Porphyrion is genuinely larger than Alcyoneus by about 7 million light-years. If Alcyoneus is 163 Milky Way galaxies lined end-to-end, Porphyrion is approximately 230. 230 Milky Way galaxies in a single row, all of it generated by one black hole, one accretion disk, one pair of relativistic jets over the course of perhaps 1 billion years of continuous activity. Porphyrion is also more distant than Alcyoneus. While Alcyoneus sits about 3.5 billion light-years away, Porphyrion is located approximately 7.5 billion light-years from Earth. This means we're observing it as it existed when the universe was only about 6.3 billion years old, less than half its current age of 13.8 billion years. The universe, then, was a different place. Denser, with the cosmic web's filaments packed more closely together, the spaces between them smaller than they are today as the universe continues its expansion. This context makes Porphyrion's size even more astonishing. In the younger, more compact universe of 6 billion years ago, the cosmic voids between filaments were smaller than they are now, and yet Porphyrion's jets had already grown to span roughly 2/3 of the radius of one of those voids. To say that another way, this single galaxy's output reached across a significant fraction of the largest empty spaces in the universe of that era. The scale at which black hole jets were operating, and may have been operating throughout much of cosmic history, was apparently far larger than the field had appreciated before Porphyrion's discovery. The implications ripple outward in multiple directions. Until Porphyrion was discovered, most of the known giant radio galaxies were found relatively nearby in cosmic terms, in what astronomers call the recent universe. The conventional assumption was that these enormous jet structures were primarily a phenomenon of more recent cosmic epochs, when the eyed universe was older, and the intergalactic medium had thinned out enough to allow such extreme expansion. Porphyrion upended that picture. It showed that even in the early universe, when everything was denser and more compressed, black hole jets could grow to scales that rivaled or exceeded the cosmic web's own structural features. Even more striking was what the LOFAR survey revealed alongside Porphyrion itself. The survey wasn't just finding one record breaker, it was finding them by the thousands. In the portion of the northern sky surveyed so far, representing about 15% of the total sky area LOFAR will eventually cover, the team identified more than 10,000 distinct jet systems spanning at least 1 megaparsec in length. 10,000. To put that in perspective, before the modern LOFAR surveys began, Roughly 1,000 giant radio galaxies were known in the entire astronomical literature, accumulated over decades of observations. LOFAR revealed 10 times that many in a single partial survey, and Porphyrion was the largest among them. We may be looking at the tip of the iceberg, OAE said at the time of Porphyrion's announcement. The suggestion is that giant jet systems, previously considered rare, perhaps exotic exceptions, may actually be far more common than anyone thought. If so, the energy they're pumping into the intergalactic medium over the history of the universe may be correspondingly larger than previous calculations assumed. And that changes things. The power output of Porphyrion's jets has been estimated at about 10 to the 39th watts. That's a 1 followed by 39 zeros, equivalent to the energy output of trillions of suns combined, sustained over perhaps 1 billion years. The black hole at the center of Porphyrion's host galaxy likely consumed approximately 1 solar mass of material per year for that entire duration. To keep that going requires a remarkably stable and continuous supply of infalling gas, sustained on timescales that challenge our models of how active galactic nuclei behave. Most active galactic nuclei are thought to go through periods of activity interspersed with quiet phases, like a volcano that erupts periodically but spends most of its time dormant. Porphyrion's existence suggests that some black holes can maintain their jets at high power for enormously long periods, long enough for the jets to grow to structures that challenge the scales of the cosmic web itself. It's worth noting that since Porphyrion's discovery, the records have continued to fall. Also, in 2024, a radio galaxy designated TXS0033+252 was found to host a radio structure extending to approximately 8 megaparsecs, about 26 million light-years, making it the current record holder as of early 2026. The fact that multiple structures of this scale are turning up in relatively rapid succession suggests that the LOFAR surveys are genuinely opening a new chapter in our understanding of the largest structures created by individual galaxies. The cosmic web, the universe's skeleton. To fully grasp why galaxies like Alcyoneus and Porphyrion matter beyond their record-breaking dimensions, we need to zoom out one more time and look at the largest canvas of all, the cosmic web. When astronomers map the positions of galaxies across hundreds of millions of light-years, what they see is not randomness. Galaxies don't scatter themselves uniformly through space like sprinkles dropped from a great height. Instead, they arrange themselves into patterns, enormous three-dimensional structures of extraordinary elegance and scale. There are dense nodes where hundreds or thousands of galaxies cluster together, bound by their mutual gravity, embedded in vast halos of hot gas. From these nodes, long filaments of galaxies stretch outward across hundreds of millions of light-years, connecting cluster to cluster like threads in the most enormous three-dimensional network ever observed. And between the filaments lie the voids. Vast, nearly empty regions of space, cosmic bubbles of near-nothingness that can be hundreds of millions of light-years across. This is the cosmic web, and it is, in a certain sense, the skeleton of everything. All the galaxies we can see, every spiral, every elliptical, every irregular dwarf, are distributed along its filaments and concentrated at its nodes. The intergalactic medium flows along the filaments like water following riverbeds, funneled toward the nodes where conditions for star formation and galaxy growth are most favorable. The voids are not completely empty. They contain a few stray galaxies and thin wisps of gas, but they are as close to true emptiness as the universe gets on large scales. The cosmic web was not always obvious to astronomers. Through most of the 20th century, the clustering of galaxies into groups and clusters was well established, but the full scope of the filamentary pattern had not yet been revealed. The first hints came in the 1980s, when large-scale redshift surveys began measuring the distances to thousands of galaxies and plotting their three-dimensional distribution. In 1989, Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics published a famous slice through the universe showing the distributions of galaxies out to about 600 million light-years. The results were immediately striking. Galaxies were arrayed along clear sheet-like and filamentary structures with large bubbles of near emptiness between them. One particularly prominent concentration of galaxies, nicknamed the Great Wall, stretched across the survey region and gave cosmologists their first vivid mental image of the cosmic web's structure. Since then, progressively larger and deeper surveys have filled in the picture. The Sloan Digital Sky Survey, which began operating in 2000 and has measured distances to millions of galaxies, revealed the cosmic web in exquisite three-dimensional detail out to billions of light-years. Computer simulations, the most sophisticated of which track the gravitational evolution of billions of dark matter particles through the full 13.8 billion years of cosmic history, reproduce the web-like structure almost perfectly when compared to observations, providing strong confirmation that we understand the basic physics of how the web formed. That physics begins with dark matter. Dark matter constitutes approximately 85% of all the matter in the universe. It doesn't emit, absorb, or scatter light. It doesn't interact with the electromagnetic force at all. We can only detect it through its gravitational effects. On the orbits of stars in galaxies, on the paths of light bending around galaxy clusters, on the large-scale structure of the universe itself. Without dark matter's gravity, galaxies would spin themselves apart. Without dark matter's gravitational scaffolding, the cosmic web as we know it wouldn't exist. In the earliest moments after the Big Bang, the universe was almost perfectly smooth. Matter distributed nearly uniformly throughout space, with only tiny variations in density. Quantum fluctuations from the first fractions of a second that inflation stretched to cosmic scales. These variations were tiny, perhaps a few parts per 100,000. But gravity is patient. Over hundreds of millions of years, regions that were slightly denser than average attracted more matter, becoming denser still, in a runaway process that eventually organized the universe into the cosmic web we observe today. Regions that were slightly less dense lost matter to their denser neighbors, becoming the voids. Dark matter drove this process. Because dark matter doesn't interact with radiation, it could begin clumping together in the early universe while ordinary matter, hydrogen and helium atoms at that stage, was still being actively scattered and buffeted by the intense radiation field of the young universe. Dark matter formed the gravitational scaffolding first. When the universe cooled enough for neutral atoms to form and radiation pressure to drop, an event called recombination, approximately 380,000 years after the Big Bang, ordinary matter was finally free to fall into the dark matter's gravitational structures. It did so along the paths determined by those pre-existing dark matter concentrations, flowing down along filaments toward the dense nodes where the biggest halos had accumulated. Within these nodes, the infalling gas heated up, cooled through radiation, and eventually condensed into the first stars and galaxies. Later generations of galaxies formed from this material, growing more complex and massive over billions of years through their own internal evolution and through mergers with their neighbors. The cosmic web grew more and more pronounced as structure formation proceeded, the filaments becoming more distinct and the voids growing, emptier as matter continued to drain out of them. The prominent filaments can reach lengths of several 100 million light-years. The voids typically range from 30 million to 300 million light-years in diameter. By volume, the universe is mostly void, far more empty space than filled space, despite the extraordinary richness of everything that does exist. And this is where Alcyoneus and Porphyrion re-enter the story with full force. Both of these structures reside in filaments of the cosmic web. Their radio lobes extend through intergalactic space, pushing through the warm, hot gas that threads along the filament, injecting energy into it, heating it, stirring it, threading it with new magnetic fields. And Porphyrion, formed in the younger, denser universe, had jets that grew to span roughly 2/3 of a void's radius, reaching from one filament almost to the next across the emptiness between. This is a remarkable statement about influence. We tend to think of galaxies as local things, bounded objects contained within themselves, affecting their immediate surroundings but not reaching across hundreds of millions of light-years to shape the large-scale structure of the universe. But if black hole jets routinely grew to the scales revealed by Porphyrion in the early universe, and the discovery of 10,000 megaparsec scale jet systems in a single partial survey suggests they may indeed have been common, then the cumulative effect of all those jets on the intergalactic medium over billions of years of cosmic history may be far larger than anyone previously estimated. Magnetic seeds and cosmic consequences. One of the most profound implications of these giant radio galaxies concerns a question that has occupied cosmologists for decades. Where does cosmic magnetism come from? Magnetism pervades the universe on all scales. Planets have magnetic fields. Stars have magnetic fields. The interstellar medium, the gas and dust between stars within galaxies, is threaded by magnetic fields. Galaxy clusters are permeated by magnetic fields. Even the intergalactic medium, the tenuous gas that fills the spaces between galaxies, shows evidence of weak but ubiquitous magnetic fields. Wherever astronomers look, they find magnetism. But the origin of these cosmic magnetic fields is genuinely mysterious. We know that magnetic fields in galaxies can be amplified and organized by processes like the galactic dynamo, essentially the rotation and turbulence within the galaxy, generating and sustaining magnetic field structures over billions of years. But a dynamo needs a seed field to start with. It can amplify an existing weak field, but it can't create one from nothing. Where did the seed fields come from? One possibility is that the seed fields are primordial, generated in the first moments after the Big Bang, perhaps during the inflationary period or during phase transitions in the early universe. These primordial fields would have been extraordinarily weak, perhaps at the level of 10 to the negative 18th Gauss, but they would have been present everywhere, seeding the entire universe from the start. Another possibility is that the seed fields were generated later by the first astronomical objects, the first stars, the first galaxies, the first active galactic nuclei. On this view, astronomical objects create magnetic fields locally and then eject them into the surrounding intergalactic medium, where they spread outward and eventually magnetize the entire cosmic web. Giant radio galaxies like Alcyoneus and Porphyrion are among the most powerful known mechanisms for injecting magnetic fields into the intergalactic medium. Their jets carry magnetic fields from the galactic environment, where fields can be quite strong, out into the intergalactic medium across enormous distances. As the jets expand into their lobes, and the lobes grow and eventually merge with the surrounding medium, those magnetic fields are distributed across millions of light-years of previously unmagnetized space. As Ohoy and his colleagues noted in the Porphyrion announcement, if these giant jet systems were common in the early universe, which the discovery of 10,000 such systems in a partial sky survey strongly suggests, their cumulative contribution to the magnetization of the cosmic web could be enormous. They may be one of the primary mechanisms by which the intergalactic medium acquired the magnetic fields we observe in it today. There's a beautiful recursive quality to this picture. The magnetic fields we measure in planets and stars, including in the Earth's own protective magnetic shield, ultimately trace back to processes in the interstellar medium of galaxies. Those processes depend on seed magnetic fields inherited from the galaxy's history. That history involves the interaction of gas falling into the galaxy from cosmic web filaments with material already present in the galaxy. And the magnetic properties of those filaments were themselves partly determined by the activity of black holes in galaxies that blasted their jets outward billions of years ago. The chain of magnetic causality reaches from the interior of our planet all the way back to the jets of ancient black holes, working through scales that span orders of magnitude. This is one of the things that makes the study of giant radio galaxies so intellectually exciting. They're not just curiosities, extreme examples of familiar processes. They're potentially important players in the physical history of the universe. The energy they inject, the magnetic fields they distribute, the heat they add to the intergalactic medium. All of this shapes the conditions in which galaxies form, evolve, and die. It shapes the flows of gas along cosmic web filaments. It shapes the thermodynamic state of the warm-hot intergalactic medium, that vast reservoir of gas at temperatures of millions of degrees that accounts for a large fraction of all the ordinary matter in the universe. Understanding giant radio galaxies is, in a very real sense, understanding the life history of the universe itself. The warming of the web. There is another crucial consequence of giant radio galaxy activity that we haven't fully explored yet. Something that connects the behavior of these distant giants to the very question of why our universe looks the way it does today, with the specific distribution of galaxies and galaxy clusters we observe. Galaxies need gas to make stars. Stars form from the collapse of dense gas clouds, so without a continuous supply of fresh gas, star formation eventually runs down and a galaxy's stellar population ages without renewal. In the early universe, galaxies were surrounded by enormous reservoirs of infalling gas. The cosmic web was actively channeling cold, dense gas down its filaments and into the galaxies forming at the nodes. Star formation rates were dramatically higher in the early universe than they are today. But over time, something prevented all that gas from continuing to flow freely into galaxies. Something heated the intergalactic medium, raising its temperature high enough that it couldn't easily cool and condense into dense star-forming clouds. Something acted as a kind of thermostat for galaxy growth, preventing galaxies from consuming all their available gas and growing indefinitely. Astronomers believe that a significant part of this thermostat effect comes from AGN feedback, the energy injected into the surrounding medium by active galactic nuclei, including the jets of radio galaxies. When a radio galaxy's jets push outward through the intergalactic medium, they heat it. The work done against the surrounding gas, the compression waves and shocks generated by the jet's passage, transfers kinetic energy from the jet into thermal energy in the gas. Over millions of years of activity, this heating can be substantial, and over billions of years of cosmic history, with millions of radio galaxies active at various times, the cumulative heating effect is thought to be significant on cosmic scales. The warm-hot, intergalactic medium, gas at temperatures between 100,000 and 10 million degrees that fills the space within galaxy clusters and filaments, bears the thermal imprint of this history. Much of the energy currently stored in this medium as heat was put there by AGN activity. The specific entropy, the heat content per unit mass, of the gas in galaxy clusters shows evidence of having been significantly boosted above what simple gravitational heating from galaxy cluster formation would predict. The excess entropy is attributed to the historical activity of active galactic nuclei, including radio galaxies. This is one of the primary reasons that the discovery of so many giant radio galaxy jets by the LOFAR surveys is scientifically significant. If there were 10,000 megaparsec-scale jet systems in just 15% of the sky, then the total number over the whole sky is much larger. And if these systems were even more common in the early universe, which Porphyrion's existence suggests, then the total energy budget for AGN feedback on cosmic scales is substantially larger than previous estimates assumed. Cosmological models of galaxy formation and evolution will need to be updated to account for this. There's something both humbling and exhilarating about this picture. These ancient, remote objects, galaxies that existed when the universe was less than half its current age, galaxies that we can only observe because their radio emissions have been traveling toward us for billions of years. These objects shaped the physical conditions that ultimately allowed life to develop. They heated the gas in cosmic filaments to temperatures that made further galaxy formation slower and more selective. They magnetized the intergalactic medium in ways that influenced the formation of later generations of stars. They carved the large-scale structure of the universe through their influence on gas flows and heating. And in doing so, they helped determine why the Milky Way is the particular size and type of galaxy it is, why it formed at the particular location it did, why it has the particular population of stars it contains. The chain of causality stretches from Porphyrion, blasting its jets across the void of the young universe 7.5 billion years ago, to the formation of our solar system, to the evolution of life on Earth, to the moment you're inhabiting right now, listening to this story in whatever comfortable place you've chosen to rest. This is not metaphor or poetic excess. It is, as best as modern astrophysics can determine, the actual physical history of the universe. The technology of discovery. It's worth pausing for a moment to appreciate the technological achievement that made these discoveries possible, because the instruments and methods involved are genuinely extraordinary in their own right. LOFAR, the low-frequency array, represents a philosophical departure from the traditional vision of a telescope. For most of the history of astronomy, bigger meant better in a fairly literal sense. A bigger mirror or dish could collect more light or radio waves, allowing fainter and more distant objects to be detected. This drove telescope builders toward ever larger single instruments. the 400-foot steerable dish of the Green Bank telescope, the 1,000-foot fixed dish of the old Arecibo Observatory, the half-mile diameter of the FAST telescope in China. These are extraordinary instruments, products of remarkable engineering. LOFAR takes a different approach. Instead of building one large instrument, it distributes tens of thousands of simple, cheap antennas across a continent and connects them with fiber optic links so that their signals can be combined digitally at a central processing facility. The result is an effective telescope diameter of nearly 2,000 kilometers, roughly the distance from the Netherlands to Poland, achieved not through any single engineering marvel, but through the careful combination of many modest components. The core of the array sits in the northeast Netherlands, in the flat, marshy landscape of Drenthe province. There, at a site near the village of Exlu, what LOFAR describes as a radio dark nature reserve, a place where mobile phone signals are deliberately suppressed to protect the sensitive antenna environment. The densest concentration of LOFAR antennas listens to the low-frequency universe around the clock. The antennas look nothing like the dishes of conventional radio telescopes. They are simple crossed dipole elements, roughly meter scale in size, arranged in fields and mounted on low frames. They have no moving parts whatsoever. They don't track objects across the sky. Instead, the direction of the telescope's beam is steered electronically by adjusting the timing with which signals from different antennas are combined. The telescope can look in multiple directions simultaneously, can repoint in milliseconds, and can observe different parts of the sky at the same time. The data volumes generated by LOFAR are enormous. Each antenna station produces streams of data at gigabits per second. The correlator at the central processing facility must handle all of this simultaneously, combining and cross-correlating the signals from dozens or hundreds of stations to produce the final radio images. The computational challenges are themselves extraordinary, requiring purpose-built supercomputers and petabytes of storage. The LOFAR 2-meter sky survey, LOTSS, which produced the images in which Alcyoneus and Porphyrion were discovered, is an ongoing effort to map the entire northern sky at low radio frequencies with unprecedented sensitivity. Each pointing covers a region of sky roughly the size of a dinner plate held at arm's length, and the full sky requires many thousands of such pointings. The sensitivity of LOFAR is genuinely revolutionary. At the frequencies it operates, between 10 and 240 megahertz, it can detect sources that are far fainter than anything previous radio telescopes at these frequencies could observe. This is what allowed Alcyoneus to be detected. Its lobes were too faint and too diffuse for earlier instruments to pick out clearly against the noise. Only with LOFAR's combination of sensitivity and angular resolution could those enormous gossamer structures be resolved and identified. And the impact of LOFAR on our knowledge of radio galaxies has been dramatic. Before LOFAR began its systematic sky surveys, roughly 1,000 giant radio galaxies were known in the entire astronomical literature, objects with radio structures extending at least 700,000 light-years, accumulated over decades of observation with many different telescopes. The LOTSS survey, covering only 15% of the sky, has already yielded more than 10,000. The total for the full sky, when the survey is complete, is likely to be far higher still. The success of LOFAR has also driven planning for even more powerful instruments. The square-kilometer array, currently under construction in South Africa and Australia, will extend the low-frequency radio revolution to the entire southern sky and beyond, with even greater sensitivity and resolution. When SKA comes online in its full form, the discovery pace for giant radio galaxies and other extreme objects is expected to accelerate further. IC 1101 and the galaxy size conversation. Before we continue with the deeper implications of Alcyoneus and Porphyrion, it's worth pausing to address a question that often arises whenever giant radio galaxies make the news. What about IC 1101, which many sources have called the largest known galaxy? The relationship between these objects tells us something important about how we measure and categorize things in astronomy, and about how the same object can appear very different depending on which ruler you use. IC 1101 is a supergiant elliptical galaxy located approximately 1 billion light-years away in the Abell 2029 galaxy cluster in the constellation Virgo. It is genuinely, spectacularly large by any measure. In terms of its stellar content, it contains roughly 100 trillion stars, about 1,000 times more than the Milky Way's estimated stellar population. Its central supermassive black hole is thought to weigh somewhere between 40 billion and 100 billion solar masses, placing it among the most massive black holes ever measured. When you look at the pure, visible, star-containing region of IC 1101, it extends to somewhere between 400,000 and 600,000 light-years across, 4 to 6 times the diameter of the Milky Way. Some sources have claimed that IC 1101 extends to as much as 6 million light-years across when you include its outermost stellar halo, the thin, diffuse cloud of stars that surrounds the main body of the galaxy. But astronomers are cautious about this figure. The outer halo of a galaxy like IC 1101 grades smoothly into the surrounding intracluster light. The population of stars that have been stripped from galaxies over billions of years and now float freely between galaxies in the cluster without belonging to any particular one. It's genuinely difficult to define where IC 1101 ends and the intracluster light begins, and different measurement methods and cutoff criteria give very different answers. Radio galaxies like Alcyoneus are measured differently. When we say Alcyoneus stretches 16 million light-years, we're talking about the extent of its radio-emitting structure, the lobes of hot plasma generated by its jets. Those lobes don't contain stars. They contain relativistic particles and magnetic fields. They are not part of the galaxy in the conventional sense. They are structures produced by the galaxy, extended into the surrounding intergalactic space by the galaxy's jets. The galaxy itself, the stellar object at the center, is a relatively unremarkable elliptical galaxy with a diameter of perhaps 240,000 light-years. So, when people ask which is the largest galaxy, the answer depends on what you mean by galaxy and what you mean by largest. IC 1101 has the largest stellar extent of any galaxy currently known. Alcyoneus, Porphyrion, and CS 0033 plus 252 have the largest radio structures of any object known to be associated with a single galaxy. These are measuring different things. The radio lobes of Alcyoneus extend through intergalactic space, far beyond anything we would normally call the galaxy itself. They are the galaxy's influence, not the galaxy's body. This distinction matters for understanding what these objects actually are and why they're scientifically interesting. IC 1101 is the product of billions of years of galaxy mergers. Giant ellipticals, like it typically form through the cannibalizing of smaller galaxies over cosmic time, growing more massive and larger with each merger. Their extraordinary stellar content reflects this history of accumulated mergers. IC1101 sits at the bottom of the gravitational well of the Abel 2029 cluster, feasting on the galaxies that fall toward it and gradually becoming the dominant object in its cluster. Alcyoneus, by contrast, is interesting precisely because it seems isolated. It is not associated with a rich galaxy cluster. It's a relatively solitary elliptical galaxy sitting in a filament of the cosmic web, far from any major cluster. Its lobes haven't grown large because of any exceptional intrinsic power, but possibly because there's less material in its surroundings to stop them. In some ways, the two objects represent opposite extremes of the same fundamental dichotomy in galaxy physics. IC1101 represents what happens when a galaxy is at the center of gravity for a rich environment, pulling in everything around it. Alcyoneus represents what happens when a galaxy has enough fuel to sustain its jets for a long time, and lives in a space empty enough to let them run. Both are extraordinary. Both teach us things about the universe that we couldn't learn without them. And both, in their different ways, reveal how varied and how extreme the universe's products can be when physics operates patiently across enormous scales of space and time. Synchrotron, radiation, and the physics of the lobes. There's a beautiful piece of physics underlying the radio emission from Alcyoneus and Porphyrion, a process that bridges the laboratory and the cosmos in a way that illustrates how deeply connected our science is across all scales. When a charged particle moves in a magnetic field, it doesn't travel in a straight line. The magnetic force acts perpendicular to the particle's motion, continuously redirecting it. The result is that the particle spirals around the magnetic field lines, tracing out a helical path through the magnetized plasma. For particles moving at everyday speeds, this spiraling is unspectacular. But for particles moving at close to the speed of light, relativistic particles as physicists call them, the spiraling generates radiation. Specifically, it generates a characteristic spectrum of electromagnetic radiation that peaks at radio wavelengths for the energies and field strengths typical of radio galaxy. Lobes. This process was first described in the context of particle accelerators, machines called synchrotrons, which use magnetic fields to keep particles traveling in circular paths while radio frequency cavities boost their energies. When the first synchrotrons were operated in the late 1940s, engineers noticed that the machines glowed with a distinctive blue light, and they called it synchrotron radiation. Later, when radio astronomers began detecting powerful emissions from distant galaxies and began figuring out the mechanism behind them, they recognized the same process at work on cosmic scales. The blue glow of a particle accelerator and the faint radio emission of a galaxy 16 million light-years across are manifestations of the same physical law, operating at different energies and on very different scales. The spectrum of synchrotron radiation carries information about the conditions in the emitting region, the strength of the magnetic field, the energies of the radiating particles, and how long those particles have been radiating. This last piece is particularly useful for studying radio galaxy lobes. As a relativistic electron emits synchrotron radiation, it loses energy. Higher energy electrons lose energy faster than lower energy ones. This means that the longer a population of electrons has been radiating, the more its high-energy members have faded away, and the steeper the radio spectrum becomes. by measuring how steep the spectrum is at different points in a radio galaxy's lobes, astronomers can estimate the age of the radiating plasma, essentially mapping the history of the jet activity in space. In Alcyoneus's lobes, the spectrum is relatively steep, consistent with plasma that has been accumulating for a considerable time. The particles in the outer parts of the lobes are older. They were accelerated by the jets further in the past, while the material nearer the center is more recently energized. By combining the spectral information with models of how the lobes expand, astronomers can attempt to reconstruct the history of Alcyoneus's jet activity, when it turned on, how it has evolved over time, whether there have been periods of varying intensity. The pressures in Alcyoneus's lobes are, as we mentioned earlier, the lowest ever measured for a radio galaxy, approximately 5 times 10 to the negative 16th pascals. For reference, the atmospheric pressure at sea level on Earth is about 100,000 pascals. The pressure in Alcyoneus's lobes is roughly 200 million billion times lower than atmospheric pressure. This extraordinary tenuousness is one reason the lobes are so sensitive to the surrounding intergalactic medium. When the external pressure of the gas is comparable to or larger than the internal pressure of the lobe can be significantly shaped and sculpted by the external medium. For a typical, more compact, higher pressure radio galaxy, the internal pressure dominates, and the external medium plays little role in shaping the lobes. For Alcyoneus, the two are sufficiently similar that the cosmic Webb filament gas can genuinely mold the lobe structures in detectable ways. This is one of the reasons the discovery of Alcyoneus is scientifically valuable beyond its record-breaking status. Because its lobes are so sensitive to their environment, they act as a kind of cosmic probe, allowing astronomers to measure properties of the warm, hot, intergalactic medium that would otherwise be undetectable. The temperature and density of the filament gas surrounding Alcyoneus can be constrained by studying the shape, pressure, and dynamics of its lobes. This is information that no other currently available technique can provide for this type of environment. In this sense, Alcyoneus is not just a record. It's a new kind of instrument. The future of giant radio galaxy research. As extraordinary as the discoveries of Alcyoneus and Porphyrion have been, they represent the beginning of a chapter rather than its end. The next decade will see several major developments that are expected to transform our knowledge of these objects and their role in the universe. The square-kilometer array, which is currently under construction at sites in South Africa and Australia, is the most ambitious radio astronomy project in history. When fully operational, it will have a total collecting area of 1 square kilometer, hence the name, and will operate across a wide frequency range including the low frequencies where LOFAR has been so productive. The SKA will be more sensitive than LOFAR by a significant factor, and it will cover the entire sky rather than just the northern hemisphere that LOFAR's European antennas can access. The combination of sensitivity and sky coverage will allow the SKA to discover giant radio galaxies at greater distances, in greater numbers, and in far more detail than LOFAR has managed. Specifically, the SKA is expected to be able to study the detailed structure of giant radio galaxy lobes, their internal variations in pressure, density, and magnetic field strength, with a level of precision that LOFAR cannot achieve. This will allow much more sophisticated modeling of the jet's interaction with the intergalactic medium, producing quantitative measurements of physical conditions rather than just rough constraints. It will also enable the detection of fainter, older radio galaxy structures. The fossil lobes of jets that turned off millions of years ago, now fading and invisible to current instruments. Counting and characterizing these fossil lobes will give a more complete picture of the total energy budget of AGN feedback over cosmic history. Several other major new facilities are also expected to contribute. The DSA 2000, being planned in the United States, will survey the sky with exceptional sensitivity at centimeter wavelengths. The NGVLA, the next generation Very Large Array, will extend radio astronomy capabilities to higher resolution. Ground-based optical telescopes with advanced spectrographs will allow the measurement of the host galaxy properties and redshifts of newly discovered radio galaxies with much greater efficiency. And the James Webb Space Telescope, already operational, has been and will continue to be used to study the host galaxies of radio sources at high redshift, providing information about the stellar populations, star formation histories, and gas dynamics of the galaxies that harbor the most powerful jets. Perhaps most excitingly, machine learning and automated image analysis are transforming the rate at which large datasets can be searched for unusual objects. The combination of deep sky surveys with AI-assisted classification is what enabled the discovery of 10,000 megaparsec scale jet systems in LOFAR's Partial Sky Survey. As the surveys grow, the AI systems improve, and the teams processing the data expand, the discovery rate for new extreme objects is expected to keep accelerating. The astronomical community is genuinely uncertain what the full population of giant radio structures looks like, how large the largest can get, how many there are, how they are distributed across cosmic time, because we've only just begun to survey them systematically. There's a real possibility, perhaps even a probability, that structures larger than TXS 003 3 plus 252, currently the record holder at 8 megaparsecs, await discovery in survey data that already exists or will soon exist. The universe has not yet revealed its upper limit, if it has one, for the size of structures that black hole jets can produce. Each new record breaker has so far turned up relatively quickly after the previous one was established. The question is whether this trend represents the true state of the universe, that structures of ever-increasing scale exist and are detectable with improving instruments, or whether we are approaching some physical ceiling determined by the finite ages of galaxies, the finite ages of AGN activity, or the structure of the cosmic web itself, the ordinary galaxy at the center. One of the most striking facts about Alcyoneus, worth returning to before we close, is just how ordinary its host galaxy is. We've mentioned this before, but it deserves a more sustained appreciation because it challenges some of our intuitions about extreme phenomena. When you look up extreme achievements in human contexts, record-breaking athletic performances, monumental artistic works, groundbreaking scientific discoveries, you typically expect to find some extraordinary attribute in the underlying person or entity. The person who runs the fastest marathon tends to have an unusually efficient physiology. The composer of the most celebrated symphony tends to have an unusual facility for musical structure. The scientist who makes the most pivotal discovery tends to have a combination of unusual insight, unusual knowledge, and unusual persistence. We expect extremes to be produced by extreme underlying properties. Alcyoneus breaks this pattern. The galaxy at its center, the elliptical galaxy SD SSJ 0814 21.68 plus 52 2410.0, is, by most measures, a fairly average example of its class. Its stellar mass of 240 billion solar masses places it well below the median of known giant radio galaxy hosts. Its central black hole mass of 390 million solar masses is similarly ordinary, representing perhaps the 23rd percentile of the giant radio galaxy population, meaning roughly 77% of giant radio galaxies have more massive central black holes. Its radio power is modest. Its star formation rate is almost negligible, just 16 thousandths of a solar mass per year, suggesting a galaxy that is largely done making new stars and is living quietly off its existing stellar population. This galaxy, entirely unexceptional by the standards of its class, produced the largest structure associated with any single galaxy in the universe. And it did so not through power or mass, but apparently through a combination of longevity, keeping its jets active for an unusually long time, and favorable environment, living in a part of the cosmic web where the intergalactic medium was thin enough to allow its lobes to keep expanding. There's something quietly profound about this. The extreme achievement was not the product of extreme intrinsic properties. It was the product of persistence in the right circumstances. The galaxy didn't have more fuel, or more power, or more mass. It just kept going, in a space that allowed it to keep going for longer than its peers. And the result was a structure 16 million light-years across. Astronomers Reinout van Wieren and Martijn Oe, reflecting on this finding in the original discovery paper, noted that within the giant radio galaxy population, there appears to be no strong correlation between radio galaxy size and radio power, stellar mass, or black hole mass. This is genuinely surprising and important. It means that the property controlling maximum giant radio galaxy size is not something internal to the galaxy, not some exceptional property of the central engine, but something external. The environment matters more than the engine, at least for determining which galaxies grow the largest lobes. This shifts the scientific conversation in an interesting direction. If environment is the key factor, then understanding the diversity in giant radio galaxy sizes becomes a problem of understanding the diversity in intergalactic medium environments, the distribution of gas densities in cosmic web filaments, the flow patterns around isolated versus cluster-associated galaxies, the pressure variations across different large-scale structures. The study of giant radio galaxies becomes a probe not just of AGN physics, but of cosmic web physics. And the two are connected in ways that were not fully appreciated before Alcyoneus showed us just how connected they can be. The deep time of radio lobes. There's a human dimension to this story that deserves its own consideration. Martijn Oe, the young Dutch astronomer whose data processing led to the discovery of Alcyoneus, and who later discovered Porphyrion, represents a particular kind of scientist, one who approaches research with curiosity and originality rather than following the established tracks. He began his academic career with dual bachelor's degrees in physics and astronomy from Leiden University, earning the top grades in his first-year physics cohort. He then pursued a master's in applied mathematics at Cambridge and another in cosmology at Leiden before beginning his Ph.D. His doctoral supervisors, Hube Rutgering and Reinout van Wieren, both leading figures in LOFAR astronomy, have spoken warmly about his distinctive intellectual style, a tendency to reason from first principles rather than beginning with the existing literature, to develop original frameworks rather than simply extending what others have already done. His primary research goal when he began his PhD was to detect the cosmic web itself, to observe directly the gas that threads along its filaments. This is one of the hardest observational challenges in astrophysics. The gas in cosmic web filaments is extraordinarily tenuous and cool, making it nearly invisible at most wavelengths. OEI's approach involved searching for faint, extended radio synchrotron emission that might arise from shocks in the cosmic web. He had developed theoretical predictions for what the signal might look like and was looking specifically for that pattern in the LOFAR data. What he found instead, during that process of reprocessing and enhancing the data to maximize sensitivity to extended emission, was Alcyoneus. In his own words, when he first saw the enormous radio structure in the processed images, he didn't immediately grasp its significance. He ran his preliminary calculations and got a number that seemed too large to be right. He checked the calculation. He checked it again. He sent the email to Martin Hardcastle, and Hardcastle confirmed. This was the largest radio galaxy ever found. OEI has described the experience as a pivotal moment in his doctoral work, one that shifted his focus from the cosmic web per se to the giant radio galaxy population that turned out to be hiding in the LOFAR data in unexpectedly large numbers. He and a fellow PhD student, Raphael Moster, developed machine learning algorithms to systematically search for giant radio galaxies in the LOTSS survey data. The result was a population of objects more than 2,000 new giant radio galaxies detected in a single systematic search, far more than had been accumulated by the entire field over decades of previous work. After completing his PhD with the highest honors possible in the Dutch academic system, the designation cum laude, awarded to only a small fraction of doctoral graduates, OA moved to Caltech as a prize postdoctoral scholar. There, with access to additional telescopes including the Very Large Array and the Giant Meter-Wave Radio Telescope, he continued the work that had produced Alcyoneus, and in 2024, that continuation produced Porphyrion. What stands out in OAI's career trajectory, beyond the discovery results themselves, is the quality of attention he brings to his work. He approaches giant radio galaxies with what might be described as both scientific rigor and a kind of aesthetic appreciation, a sense that these objects are not merely data points to be catalogued, but cosmic events of genuine grandeur, worthy of careful, sustained contemplation. In interviews and public communications, he speaks about these discoveries with enthusiasm that communicates not just the scientific significance, but the wonder, the almost vertiginous sensation of understanding that we live in a universe capable of producing structures of this scale. What remains unknown? As with every great discovery in science, the finding of Alcyoneus, Porphyrion, and their kin has raised more questions than it has answered. And, in the spirit of honest science, it's worth sitting with those open questions rather than rushing past them. The most fundamental mystery remains. Why do some radio galaxies grow so large? As we've already seen, Alcyoneus's host galaxy appears ordinary by the standards of its class. Not an exceptionally massive black hole, not a particularly powerful jet, not an unusually large stellar population. The current best hypothesis points to environment, to the particular thinness of the intergalactic medium in Alcyoneus's cosmic neighborhood. But this has not been directly confirmed, and the details of how exactly the environment determines maximum jet size remain poorly understood. Relatedly, how long do these jets stay active? for a structure to grow to 16 million light-years, or 23 million light-years, the jets must operate more or less continuously for hundreds of millions, perhaps a billion or more years. But most active galactic nuclei are thought to undergo episodic activity, periods of high activity separated by quieter phases. What determines the duty cycle of AGN activity? What gives some black holes access to a fuel supply reliable enough to sustain their jets for such extraordinary periods? There's also the question of what happens to these structures when the jets eventually turn off. Radio lobes lose energy over time through a process called synchrotron aging. The relativistic electrons lose energy as they emit radiation, and eventually they can no longer radiate at frequencies LOFAR can detect. An old, faded radio lobe would be invisible to our current instruments. We're therefore seeing only the active and recently active radio galaxies, not the full population of structures that have been generated by black hole jets over cosmic history. The total number of such structures and the total energy they have injected into the intergalactic medium over the history of the universe may be far larger than even the already astonishing numbers revealed by LOFAR suggest. There's the question of magnetic fields. Are the giant radio galaxies truly responsible for seeding the magnetism of the intergalactic medium? The evidence is suggestive, but confirming it requires measurements of magnetic fields in the intergalactic medium that are at the very limit of current capabilities. The next generation of radio telescopes, particularly the SKA, will attempt these measurements, and the results will either confirm or challenge the picture we're building. And there's the deeper question of what else LOFAR and future surveys will find. What other species of extreme objects are lurking in the data, waiting for someone to look at the right angle with the right sensitivity? The history of astronomy suggests that every major improvement in observational capability reveals a new class of previously unknown phenomena. LOFAR has already demonstrated this dramatically with giant radio galaxies. What else is hiding in those petabytes of data? The view from here. Let's return, in our final thoughts tonight, to the scale of all of this. Not the overwhelming, disorienting scale that shrinks us down to nothing, but the scale that somehow enlarges us instead. There's a particular quality of feeling that comes from properly contemplating the universe's largest structures. It's something that blends awe and humility and an unexpected sense of connection. A recognition that the same physical laws that govern the fall of a leaf, the orbit of the moon, the beating of your heart, also govern the production of relativistic jets that travel for 1 billion years and fill 16 million light-years of space with hot plasma and magnetic fields. The universe is coherent. It follows rules, and those rules, applied with patience across vast scales and times, produce Alcyoneus and Porphyrion. Consider what happened for Alcyoneus to exist. A galaxy, not a particularly special galaxy by the standards of its class, formed 3.5 billion light-years away, long before complex life had evolved on Earth. At its center, a supermassive black hole began to consume infalling gas. As it consumed that gas, the physics of accretion, the heating, the magnetic fields, the angular momentum, began to organize some fraction of that gas into jets. Those jets shot outward at nearly the speed of light, and they kept doing so, continuously or nearly so, for hundreds of millions of years. The intergalactic medium in that particular part of the cosmic web happened to be thin enough that the jets could expand far without being stopped. And so the lobes grew and grew and grew, until they spanned 16 million light years. And then, eventually, billions of years after the lobes began forming, a species on a small rocky planet 3.5 billion light years away built an instrument sensitive enough to detect them. An earnest young astronomer who was looking for something else entirely glanced at the right data at the right moment and recognized what he was seeing, and a discovery was made. The universe doesn't care about our discoveries. It wasn't waiting for us, wasn't holding its breath hoping we'd notice. Alcyoneus would exist, and would be exactly what it is, whether or not any mind ever looked at it. But there's something about the fact that we did look, that our curiosity and ingenuity eventually grew powerful enough to reach across 3.5 billion light years and see. That feels worth acknowledging. We are small, vanishingly, almost absurdly small compared to the structures we're discussing tonight. A single human being occupies perhaps 2 meters of a universe that contains structures 16 million light years across. The math doesn't even bear working out, and yet here we are, describing those structures in language, understanding the physics that produced them, connecting them to the history of the cosmos and to our own existence. The capacity for understanding is itself something the universe produced, through the same patient physical processes that produced everything else. And that capacity, for all its smallness, has reached across space and time to hold Alcyoneus and Porphyrion in the mind, even briefly, even imperfectly, closing. As you drift now toward sleep, let the images we've drawn tonight continue to move at their own slow pace through your thoughts. The flat fields of the Dutch countryside, bristling with thousands of simple antennas listening to the low-frequency hum of the cosmos. The young astronomer at his computer, puzzled and then exhilarated, running his calculation 3 times because the answer seemed too extraordinary to trust. The radio lobes spreading through the intergalactic medium of a cosmic web filament 3.5 billion light years away, performing their slow dance with the invisible gas of the universe's skeleton. The scale, which is too large to truly hold, but which can be gently approached. 163 Milky Ways in a row. 230 Milky Ways in a row. 23 million light years of empty space, filled with tenuous plasma and magnetic fields, and the residue of 1 billion years of black hole activity. The question that still hangs in the air, unanswered and perhaps unanswerable for now. Why here? Why this galaxy, this environment, this particular thread of the cosmic web? Why did Alcyoneus grow to the largest structure any galaxy had ever been known to produce? We don't know, and there's something comfortable in that not knowing. A reminder that the universe is still full of mysteries, still offering questions that no one has yet answered, still capable of surprising even the scientists who have spent their careers staring at its most extreme phenomena. Every answer we find opens new doors. Every record that falls is replaced by a new one to explain. The universe is not running out of things to teach us. Let your mind drift now, as galaxies drift through the cosmic web, slowly on timescales so vast that a human lifetime is a flash. Let the images of those enormous lobes, those cosmic wings spreading through the intergalactic dark, carry you gently toward sleep. You are very small. You are very far from Alcyoneus, and you are made of the same atoms, governed by the same physics, connected by the same 4 billion years of cosmic history. That connection doesn't shrink the universe. It makes it feel, somehow, a little more like home. Good night. If you found this journey through the cosmos restful and enriching, please consider leaving a like and subscribing to the Science Pillow. Every subscription helps us keep making content that invites you to rest, wonder, and drift off to sleep with something beautiful in your mind. And if you have a topic you'd like us to explore, a question about the universe you've always wanted answered in the most peaceful possible way, leave a comment below. We read everything, and your curiosity is what shapes what we make next. Sleep well.